All right, let's do this. So here we go. Hopefully Zoom will cooperate with me here. All right, so today we are going to talk about non-rolling conservation of energy problems. We've done conservation of energy problems, right? Things sliding down a ramp, roller coaster problems. We've done conservation of energy problems where things roll, like a ball rolling down a hill or something. This time we're going to do objects that deal with rotational kinetic energy and our conservation of energy problems, but aren't about objects rolling. What are you talking about, Mr. Hecker? I'll show you what I'm talking about. Bam! Look at this. Here we have a pulley. The problem tells us that the pulley is disc-shaped. So pulley, what do we know about the pulley? We know that it is disc-shaped, in which case the rotational inertia of a disc-shaped pulley about its center of mass is 1/2 m, where m is the mass of the pulley, times r squared, where r is the radius of the pulley. All right, and the problem tells us that our pulley does in fact have a mass of m. It doesn't tell us the radius, so I'm going to just assume that it is lowercase letter r. All right. Okay, so that is that. In this problem, we also have this block. Well, let's use, how about a nice green? I feel like green doesn't get used enough. We've got this block here. And the block, the problem tells us, has a mass of m. All right, and so the whole premise behind this thing is that we've got a rope which goes around the pulley and then down to the block. All right, both the block and the pulley begin at rest, and we're going to drop it. And what's going to happen is the block is going to fall downwards through a distance x. And what I would like you to tell me is the velocity of the block when it gets down to here. So we will call that v, which is sort of like the final velocity, right? So after it falls a distance x, what is the velocity of the block? That is what we are trying to find here. Okay, so it turns out that here, because there are no external forces, there's really nowhere for the energy to go. So our total energy has to stay the same. Okay, in the past, more often than not, we have solved conservation of energy problems by looking at the total energy before and saying that that's equal to the total energy after, right? Or I guess in AP speak, we would say the mechanical energy initially is equal to the mechanical energy final, right? But more recently, we've been solving problems by, instead of saying that the total doesn't change, no, but I guess this is the same way. So another way of writing this would be to say the change in total energy is 0, right? And I more and more am starting to think that that really is like the better way to solve these problems, all right? So that's how we're going to go about this. In this problem, our total energy is not changing. That means the change in total energy is 0, which for us means that if 0 is the change in total energy, well, what do we mean by the change in total energy? Well, that's the change in GPE, right? Because the block is going to move down. So there's a change in GPE for the block. There's a change in kinetic energy because as the block moves, it speeds up. But there's also a change in rotational kinetic energy for the pulley. Okay, so all of these changes have to add up to 0. Okay, so that's the whole premise behind this problem. Okay, let me do this. I'm going to change my screen layout here for a minute. Let's go to 2-page. And let's click this guy. There we go. All right, so change in GPE of the block. Well, it's mg times change in height, right? So the mass of the block is m, g is g. Our change in height is -x because our block is going to go down a distance of x. Okay? The change in kinetic energy for the block. Well, since it starts at rest, that's going to be the same as the final kinetic energy, right? So that's just 1/2 mv squared, right? Because we're going to achieve a velocity of v, which is what we're looking for. All right. Finally, rotational kinetic energy of the pulley. Well, again, it starts at rest. So the change in rotational kinetic energy of the pulley is equal to the final rotational kinetic energy of the pulley, right? Because you start at 0. All right. So this is 1/2 times the rotational inertia of the pulley times the angular velocity of the pulley squared. So that's 1/2 times 1/2 mr squared times, I don't like that omega. So here's the deal. If I had done a better job writing this problem over here, I would have told you that the string does not slip on the pulley. All right, which is important because what that means is if the block is moving down at some velocity v, that means the rope is moving at some velocity v, which means a point on the outside of the wheel is moving at a velocity of v, which means I can use a jumper equation. And I can just replace omega with v over r is omega. Don't forget it's squared. Haha, my r's cancel. So 1/2 times 1/2 is 1/4 mv squared. Sorry, my v sort of looks like an r. Let's fix that. V squared. And that's my change in RKE. All right. And so the idea is all of these guys have to add up to 0. So here we go. This and this and this have to add up to 0. So mg times x, but the x is negative, plus 1/2 mv squared, plus 1/4 mv squared has to add up to 0. So this is 3/4 mv squared. Out of my way, thingamajig. Has to equal, I'm going to add the mgx to both sides. And then just solve it. M's cancel, multiply by 4/3. Square root of 5. There you go. There is the velocity. I don't know why I did that at you. Okay, so not rocket science there. I think that the big thing here is, I don't know, maybe you're watching this 5 years in the future, and maybe I've fixed this, but I think that more and more I'm going to start encouraging my AP students to solve conservation of energy problems instead of thinking about this, to replace that with thinking about this, where you just add up your different changes and set it equal to 0. All right. And I may start teaching honors that way. And if you learned it that way in honors, then I've become a better teacher than I was when I recorded this video you're watching right now. All right, cool. I guess that's everything on that one. Number 2. All right. So here what we've got is we've got a pendulum, which is starting in this orientation, and then it's going to swing down. Okay. And so the idea is let me get a thing. Here we go. Here's a thing. So we've got a pendulum, and it's going to swing down like that, right? All right. And so the idea is as it swings down, it's losing gravitational potential energy, right? And in return, we're gaining rotational kinetic energy, right? Okay, but so this raises a couple issues. One, how do we deal with the change in gravitational potential energy, right? Because different points on my pendulum are undergoing different changes in height. Okay, so when you've got an object like this that is swinging vertically instead of just moving vertically, like here, it's easy to do the change in height, right? Because every particle on it is going up or down the same amount. But here, different particles are going up or down different amounts. So to consider the change in GPE, you consider the change in height of the center of mass. I'm going to say that again because it's super important. The change in GPE is determined, that's abbreviation for determined, not Detroited, is determined by the change in height of the center of mass. Okay, that's issue number 1. Issue number 2 is we're gaining rotational kinetic energy. okay? So if it was doing this, that would be kinetic energy. If it was doing this, it would be rotational kinetic energy. If it was doing both, then you'd have both kinetic and rotational. But because we've got some points that have no velocity, right? There's no velocity here. And other points that have more velocity, right? The farther out you go, the more the velocity is. We can't think of it in terms of just linear velocity because different points have different velocities and that complicates things. So we use rotational kinetic energy. All right. So, that's that. All right. So, I guess let's kind of run through this here. And let's see what we can do here. So we've got a pendulum. It's made of a uniform disk. Let's see, calligraphic pen. All right, so the uniform disk of mass m and radius r. Radius r, mass m, is attached to a uniform rod of mass 2m and length 6r. We'll do that in green. How about? Uniform, oh, that's not what I wanted to happen. Undo. Uniform rod of mass 2m and length 6r. 6r, 2m. All right. It's held horizontally at rest and released, so it's going to swing down like this. All right. And so again, really the only force here is gravity. So our total energy should stay the same, which means our change in total energy is 0, which means if you add the change in gravitational potential energy and the change in rotational kinetic energy, you have to get 0. Okay, so let's do this. Nope, wrong one. Change in GPE is equal to the mass of, you know what, I'm going to come up with a quick list of letters here. So little m is going to be mass, big R is going to be radius, little r is going to represent rod, as in the mass of the rod. D is going to be disk, as in mass of disk, and P is going to be the pendulum itself, like the whole pendulum, and that will be as in mass of pendulum. Okay, so I'm going to use some shorthand over here. All right, so the change in GPE is equal to the mass of the pendulum times G times the change in height of the center of mass of the pendulum. All right. So we need to find the position of the center of mass. So the idea is our center of mass is going to be here. And as it swings down, then our change in height will be the same as that position of the center of mass, right? Because it starts, you know, up here and it's going to go down to here. So this distance is the same as this distance. Okay, so let me clear up my board so it doesn't get too scribbly before I get ahead of myself. So the position of the center of mass of the pendulum is equal to the position of the disk times the mass of the disk plus the position of the rod times the mass of the rod over the mass of the disk plus the mass of the rod. So position of the disk. Well, I got to find the center of mass of the position of the disk, right? So it makes sense that we want to call this a position of 0. So if the whole rod is 6r, then this must be 5r, right? So I'm going to go 5r times the mass of the disk, which is m, plus, now we got to do the rod, so we'll do that in green. No, green. Let's see, the position of the rod. Well, the whole rod is a length of 6r. Its center of mass is going to be halfway along that, which will be 3r. Times the mass of the rod, which is 2m. And then we have to divide the whole mass by mass of the disk is m, mass of the rod is 2m. So simplify this, all of your m's cancel, and you end up getting, well, so on the top, I'll just write it out. On the top, you get 11 mr. On the bottom, you get 3m. So this gives you 11/3 r. So that means that my center mass is going to go from here to here. And as a result, means the change in height of the center of mass of the pendulum is negative 11/3 r. Okay, so that is that. Now, so that will help us find our change in GPE. Now we need to deal with our change in RKE. So change in RKE is 1/2 times the rotational inertia of the pendulum times the angular velocity squared. All right. Quick comment about the way I worded this question. I changed it and then changed it back, and it resulted in a typo. It says, what's the angular velocity of the center of the disk? Well, the angular velocity of any point is the same, right? So I should have just said, what's the angular velocity of the pendulum? All right. So the rotational inertia of the pendulum is equal to the rotational inertia of the rod plus the rotational inertia of the disk. So the rotational inertia of the rod is easy because it's just a rod about its end. So in general, a rod is 1/3 mr squared, where r is like the length of the rod. But here, our mass is 2m and our length is 6r. So the rotational inertia of the rod is 1/3. Oops, try that again. 1/3 times the mass of the rod times the length of the rod. Oh man, times the length of the rod squared. So this ends up giving you 24 mr squared. All right. Then for the disk, the rotational inertia of the disk, well, that's equal to the rotational inertia of the disk about its center of mass plus mh squared, right? We have to use the parallel axis theorem. If the disk was just rotating about its center, we'd be good. But it's not. It's rotating about a point way over here, a distance of 5r away. So that's our h, right? So the rotational inertia of a disk about its center of mass is 1/2 mr squared plus mh squared. That's m times 5r squared. Again, that's the parallel axis theorem. So simplify this, and you end up getting 25.5 mr squared. And so now we can find the rotational inertia of the pendulum, because it's just rod plus disk, which gives you 29.5 mr squared. So now, here we go. Change in GPE plus change in RKE has to be 0. So our change in GPE is the mass of the pendulum times G times our change in height. Right? Remember, that was the center of mass of the pendulum. Plus our change in RKE, which is 1/2 times I times omega squared. Shoot, I added wrong, didn't I? 24 plus 25 is 49.5. Sorry about that. Mr squared. Okay. Oh, and then so this all has to add up to 0. So let's see. I'm going to take, well, okay. So this mess, I'm going to add it to the other side to make it positive. And I can cancel some stuff. So this looks to me like I'm going to get 11 mgr on the right side of the equation when I add it to both sides. And then on the other side, I get half of 49.5, which I believe is 24.75 mr squared omega squared. So now we can cancel some stuff. We are almost done. Look at us go. This is like my 4th time recording this video because I had tech issues. I hope I'm not going way too fast. So the m's cancel. This r cancels one of these r's. So now I can just divide and I get omega squared equals 11g over 24.75 r, and then you can take the square root. There you go. There's the angular velocity of the rod. And then if you wanted to find the velocity of a point on the rod, you just plug your numbers in. Plug your radius in. Oh, wait. No, I'm wrong. You couldn't. R is a fixed number, right? That would be the length of the rod. So if you wanted to find the velocity of a point on the rod, you'd take omega and multiply it by the radius for that point. I wish I hadn't just said that because I think I confused it. Too many R's. All right. Anyway, I think you're good. If not, ask me when I see you in class. Good work. Oh, looking at the wrong camera. Where's the stop share? Where's the stop record? Goodbye.